How are autonomous robots able to navigate in an unknown environment? Simultaneous localization and mapping, or SLAM, is a technique used by autonomous vehicles to build and update a map and find their location in an unknown environment. Our robot uses SLAM to help it navigate even with very noisy data. The goal of our project was to create a robot capable of navigating a walled environment, shooting a laser at green targets, and returning to its starting position when it is finished exploring. Most of our data for navigation comes from either encoders, an onboard camera, or an IMU. All of these devices produce very noisy data and are capable of giving us serious problems if we're too close to a wall. In order to navigate without crashing, our robot needs to know where the walls are. We used the camera for this task and created a blue line detector. Because all of the walls have blue tape at the bottom, our robot is able to see the walls by finding blue lines and projecting rays from the robot's camera to the bottom of the blue tape. We combine these points into lines and calculate their location in 3D space relative to the robot. We also use the camera to find green triangles. We do this by converting the image data to HSB, running union find on the green parts, and looking for large results where the number of pixels is approximately half the size of the bounding box. The IMU is used to determine our yaw, as it tends to return much better results for finding our current angle than our odometry data, and the error is based on time rather than our distance traveled. Our odometry uses the encoders on the two wheels to determine how far we've traveled and get our location using dead reckoning. Using this alone to calculate our angle would be very problematic, as errors in theta build up quickly when you move. To build the best map possible and determine our real location, our robot uses a graph-based SLAM algorithm. Each observation of a feature, like a triangle, puts a constraint on the graph based on the position of the feature. This constraint acts like a spring. The more certain we are of the observation, the stronger the spring is. High uncertainties result in weak constraints. By giving SLAM our odometry data and the observed feature locations, along with their corresponding uncertainties, we can solve the system to find the least error solution. One issue that creeps up is the reobservations of a feature. How do we know if the feature is a new feature or a previously observed feature? This is the problem of data association. We solve this by taking the Mahalanobis distance between the new feature and previously observed feature, and this helps us decide whether they are the same. We can see that the map created very accurately resembles the real world and allows us to decrease the effects of noise. This helps us get a much better understanding of our current position and our environment, which helps our robot explore and meet the goal.